Hello all, welcome back. Today we will be starting our new topic out of your rocket aerospace propulsion. We will be starting with your solid propellant rocket motors. Now, let us understand what do you mean by solid rocket propellant motor. Now, anything particularly, what we will just break it down. Solid propellant rocket motor, right? We know what do you mean by rocket motor. Rocket motor is nothing but your combustion chamber with nozzle. Now, what do you mean by this part is nothing but the type of propellant that you are storing or you are using onto the rocket motor. So, in our case, now what we are considering is basically a solid propellant, means the propellant which we are considering is of solid in nature, right? Solid in nature while burning, right? So, collectively, those are called as solid propellant rocket motors. Now, why solid propellant? Because it is storable and relatively safe to handle compared to your liquid propulsion systems. We will come to liquid propulsion system in furthermore. Now, and there are no propellant delivery system is required, which produces a huge improvement in reliability as well as the cost. The two main disadvantages are that the motor cannot be controlled once it's ignited, although the thrust profile can be preset, and the specific impulse is rather low because of the low chemical energy of the solid propellant. Right? Now, what are the two main disadvantages? Is the motor cannot be controlled once it has been ignited. Means once you are starting up or you are burning your propellant initially, it continues to burn till all the complete propellant, all the solid propellant is burnt up, right? And what is the second disadvantage? Is nothing but the specific impulse. As we discussed previously, that the specific impulse is dependent on the chemical energy as well as the mass flow rate that is occurring through the nozzle. Now, due to the low chemical energy that is being generated by the solid propellant, the specific impulse would be low. Now, thermodynamically speaking, a solid fueled rocket motor is identical to your liquid fueled engine. What? Basically, a propellant, combustion chamber, a nozzle. Right? Now, in case of the liquid as well as solid. Now, in case of solid, what happens in the propellant casing? This will be my propellant, solid propellant inside my combustion chamber. Whereas for liquid, what happens? There will be separate partitioning for oxidizer as well as fuel. These are pumped separately into my combustion chamber, then burned through the nozzle. Right? The hot gases, right? Both will have the hot gases that are produced by the combustion, which is converted into my high-speed exhaust stream, and exactly the same way. So the nozzle and the throat, the restriction in the combustion chamber leading to the throat are all identical in the form as well as the function. The thrust coefficient, that is calculated in the same way as for liquid fuel engine, as is the characteristic velocity. The hot gases that are being produced by the combustion on a hollow surface of a solid fuel block, also known as a charge or a grain. In the most cases, the grain is bonded to the wall of the combustion chamber to prevent access of hot combustion gases to any surface of the grain not intended to burn, particularly which to prevent the heat damage to the combustion chamber walls. Now, let us understand a grain. Right? In a solid rocket propellant motor, if this is my casing, right? After casing, what you will be having? You will be having some amount of binder or some form of adhesive, right? Then you will be having all the propellant that you are intending to burn, right? All the propellant that you are intending to burn. Now, this particular section of burnable propellant is called a charge or a grain. Particularly, it's nothing but simple fuel block. Now, as the fuel block, right, these are bonded to my wall of the combustion chamber, which prevents the access of hot combustion gases that it burning to the any surface of the grain that is not intended to burn. Now, the grain, particularly the solid fuel block, contains both fuel as well as the oxidant that is finely divided in a powdered form and mixed together and held by a binder material or an adhesive, right? Now, this is for as an example for a solid rocket motor. Now, what we will see, we will understand the components. First thing, the nozzle as well as the throat are very similar to your liquid propellant rocket engines. Next will be your casing, which holds the grain or the charge or the solid fuel block. Next one will be my igniter, through which I will be starting my combustion process. Next one will be my burning surface. The burning surface is the area where the initial burn starts, as well as continuously progressed accordingly to the shape of my grain, right? In our case, there are multiple shapes through which a burning surface or the area of burn can be increased or decreased based on the requirements of the manufacturer. So, in our case, if I am putting a star shaped, right, a star shaped burn, as soon as the initial igniter burns, it tends to burn the areas which are open towards it, right? Now, as it goes on burning, right, after a period of time, these tend to burn from inside out. So, in the lateral direction of my casing, they tend to burn out, right? After a period of time, what happens? You will be left with small amount of propellant on the casing, which clears my solid fuel. Now, as the solid fuel is completely exhausted or done, then you can easily remove or you can easily discard the stage or the solid rocket motor. Now, the fundamental simplicity of a solid rocket propellant rocket enables a wide application. The exhaust velocity is not very high. The most advanced types produce about 2700 meter per second, but in the absence of turbopumps as well as separate propellant tanks for oxidizer as well as the fuel, and a complete absence of complicated valves as well as pipelines, can produce a high mass ratio or low cost of the both. In addition, the reliability is very high, but due to a small number of individual components compared with a liquid fueled engine. The one very big disadvantage is that the device cannot be test fired, or so the reliability has to be established by analogy or by quality control. There are two areas in which solid motors excel are as a strap-on boosters and as an upper stages, particularly for orbital insertion or for circularization of elliptical transfer orbits. Solid propellants are by definition storable. Now, as a booster, a solid motor can have a very high mass flow rate as well as high thrust, while the engineering complexity and the cost can be low in a single use item. This is ideal for early stages of launch where the high exhaust velocity is not an issue. And to produce the same thrust with a liquid fuel rocket engine would not require much larger engine because of the higher specific chemical energy of some liquid propellants, but it would be more costly as well as a less reliable method. Very large solid boosters can be made and fueled in sections which are bolted together, which again makes a simplicity for construction and storage of what otherwise would be requiring a larger unit, right? Let us understand this a bit. Now, what happens in case of the rocket boosters? We can basically create or basically use for as a strap-on boosters, right? In your previous class of the same aerospace propulsion, what we have discussed your multi-stage rockets, right? And a multi-stage rocket, we have discussed regarding the boosters, right? Boosters which enable us to provide high thrust initially at sea level, right? High thrust initially during the sea level, then after the initial launch over a period of time, what happens as soon as they are done, we will be discarding them similar to your space shuttle missions as well as Ariane 5 rockets, then upon which the overall mass will be reduced, right? The overall mass ratio would be reduced. Now, based on this, what happens? The velocity of the vehicle, particularly the rocket vehicle, would increase drastically. In the same way, what we can use the solid rocket motors as a strap-on boosters. Now, coming to this, very large solid boosters can be made as well as fueled in sections, right? As we know, the propellant, particularly the solid propellant, is a mixture of finely grinded oxidizer plus fuel in certain proportions according to the manufacturer's discretion. Now, these can be created as sections, then added to form a larger booster as on when required, right? Now, what happens is, as the liquid, the oxidizer as a fuel is not reactive in nature during normal ambient temperatures, we can stack them up one above the other to form a larger section of rocket in such a way that it can be easily mounted or easily configurable. Now, as a final stage, the rocket motor is again reliable as well as well adapted to its high mass ratio. While the dead weight of a liquid stage includes turbopumps, empty tanks as well as two separate propellant tanks, the dead weight of the solid stage is just a casing as well as a nozzle. The casing for upper stage is often made of composite materials to reduce the overall mass for that particular stage even further. It is also convenient to make such a stage with spherical or quasi-spherical form so as to minimize the mass of the containing walls. Now, we will undergo the steps or the method on which we will be designing a solid rocket motor. Now, the solid rocket motor is very simple and the design issues are therefore fewer because there is no injector or there is no propellant distribution system. The design issues related to the propellant are mostly concerned with the selection of the propellant type and the mounting as well as the protection of the propellant in the casing and a small ignition that is similar to the liquid fueled engine. There are no propellant tanks, but the casing has to contain the propellant and also behave as a combustion chamber. Why? Is basically the same example what we have taken earlier. Right? What happens? The simple rocket motor, as the signal comes for igniter to ignite the charge, it tends to burn the surface that is exposed to the ignition area or the ignition flame. Now, as soon as the ignition takes place, what happens? They tend to burn laterally, right? So, there is no other separate area to store the propellant as well as to combust. So, whenever the combustion takes place, that occurs inside the casing, and after the burning is done or the combustion is done, the same gases are passed on to my CED nozzle or my rocket nozzle, and right after at the throat they are expanded through supersonic power. Now in this case there are no propellant tanks, but the casing which stores the propellant tanks will be also acting as a combustion chamber. And for boosters the casing is large, and to combine the large size with the resistance to high combustion pressure is very different from the same issue in the liquid system where the requirements are separated. The cooling is totally different because there are no liquids involved and the heat dissipation is entirely passive. The combustion instability for which a liquid fueled rocket is dependent only on a steady supply of propellant. Once the chamber and the injector have been optimized, is very complicated for a solid rocket propellant. The supply of combustible material is dependent on the condition of the combustion chamber, and there are increased chances for instabilities to arise and propagate. And this stability is associated with the stability is my thrust control. And for a liquid rocket, the thrust is actively controlled by the rate of supply of propellant, whereas it is majorly cases it is stabilized using a constant value, particularly as particular volume of my fuel or as oxidizer into the combustion chamber. But for a rocket engine, particularly the solid rocket, the thrust depends on the rate of the supply of combustible propellant. Right? It depends on the pressure and the temperature at the burning surface, and it cannot be actively controlled. Let us understand a bit. This is my oxidizer fuel. These are my turbo pumps. These are my valves. Right? Combustion chamber, nozzle. Now, what happens with respect to my liquid fuel engine is whenever we are designing, we will be having some elements, particularly the valves as well as the turbo pumps or the piping to hold the liquid fuel as well as the oxidizer towards the combustion chamber. That we can control basically the valves and the speed of the turbo pump to have a certain amount or certain degree of freedom to control the degree of or the control the amount of propellant that's being entering into the combustion chamber. That in turn directly controls my thrust as well as the stability of my aircraft as and when required. Now, but when a solid propellant rocket motor is considered, what happens during this is basically once it is being burned, right, based on the burning area, right, based on the burning area, the temperature as well as the pressure it is being burned depends or reflects the thrust, right, the thrust that the rocket develops, and based on the thrust again the stability is being associated. Now, what happens in comparison to both? The liquid propellant rocket motors are more stable or more controllable rather than solid rockets. In the same way, the liquid fuel engines can be shut down, as we have discussed, by closing the valves that supply the propellant, whereas for a solid motor, it continues to thrust until the propellant is exhausted, right, until unless there is no propellant left inside the casing. And these design problems are central to correct performance of a solid rocket propellant motor. When a solid fuel rocket is essentially a single use item, the cost of boosters is very large, and the necessary engineering quality for some components, specifically the casing, may make them suitable for the use. Now, considering the propellant composition, rather than selecting a particular propellant of a particular purpose, each rocket propellant manufacturer has its own optimized propellant mixture, and the basic solid propellant consists of two or more chemical components which react each other to produce heat as well as gaseous products. Now, the solid propellants have been used since the earliest times, and until 20th century, they were basically the gunpowder as well as a mixture of charcoal, sulfur as well as saltpeter. And a modern propellants which do not differ from the fundamental form these early mixtures. The oxidant, which is usually the one of an inorganic salt such as potassium nitrates, also called as saltpeter, although chlorates and perchlorates are now commonly used. The fuels sometimes also include sulfur or carbon in the present form in terms of as an organic binder. As with any other type of rocket, the aim is to achieve the highest combustion temperature together with the lowest molecular weight in the exhaust. And the difficulty with the solid oxidants is that they are mostly inorganic and contain metal atoms, and these lead to a higher molecular weight molecules in the exhaust. So, similarly, the solid fuels generally have a higher atomic weight than hydrogen. So again, the molecular weight in the exhaust is driven up. The chemical energy per unit mass of propellant can be same for as the main liquid propellants. So the combustion temperature is similar. But a particular problem is that some of the combustion products may form solid particles at an exhaust temperature. And again, this affects the performance of nozzle in converting heat energy into gas flow. All of these properties affect the performance of the solid motors. The charge or the fuel block of the solid rocket motor is often called as the grain. As we know, the basic components of the grain are nothing but my fuel as well as oxidant primarily, and binder as well as additive to achieve the burning stability as well as a stability under storage. The finished charge must also be strong enough to resist the forces induced by the vehicular motion and the thrust. It must also be thermally insulating to prevent parts of the grain other than the burning surface from reaching the ignition temperature. In the past, two different kinds of solid propellant have been used. First kind is a mixture of an inorganic oxidants with fuels. This is the most commonly used today, as well as the other type is based on nitrated organic substances such as nitroglycerin as well as nitrocellulose. These came into use as gun propellants after gunpowder, and it was natural that they should be considered as rocket propellants. These materials have the property that they contain the oxidants and the fuel together in a single molecule or a group of molecules. The heat that induces a reaction in which the complex organic molecule which break down or reduces to produce the heat as well as the gaseous oxides of nitrogen, carbon as well as hydrogen. The molecular weight of such gases mixture is rather low and giving an advantage in terms of exhaust velocity. These propellants are termed as homogeneous propellants. They are not used for launcher boosters but most orbital change motors. They have been superseded by more advanced mixture of propellants that we will be discussing further. The fundamental requirement is to develop the highest thrust per unit mass, right? And this requires a high combustion temperature and a low molecular weight of the combustion products. In general, a relatively high temperature of the combustion is easy to achieve, but it is possible we have a same low molecular weight of the products achievable with liquid hydrogen as well as the liquid oxygen as propellant, and the presence of carbon and byproducts of inorganic oxidants, potassium and sodium salts produces a higher molecular weight, hence a lower exhaust velocity for my solid rocket propellant motors. High molecular weight doesn't prevent the solid motors from developing the high thrust, which is just a matter of high mass flow in the throat area. The high ultimate vehicular velocity is harder to achieve with a solid motor because of the low exhaust velocity and a typical value of 2700 meter per second. For final stages, optimization is directed towards improving the mass ratio rather than exhaust velocity. In modern propellants, metallic powders are often added to increase the energy release and hence the combustion temperature. Aluminium is usual, and in the case of exhaust products that contain aluminum oxide, which has a high molecular weight and is refractory. So, in the form of small solid particles, these are added. Particles in the exhaust stream reduce efficiency. They travel more slowly than the surrounding high velocity gas and they radiate heat more effectively as a black bodies and therefore reduce the energy in the stream. Right? Let us elaborate on this. So what we will be having basically in a solid rocket motor, oxidizer plus fuel. These are your major components. Along with this, what we will be having? We will be having binder plus additives. These are added in order to enhance the stability as well as enhance the performance of my rocket motor. Now, what happens in this? As a part of additives, we will be adding metallic powders, particularly for example ALO2 or ALOX, aluminum oxide. Now, what are the properties of aluminum? Is basically is a refractory material which produces more amount of heat. Now, as it contains its own oxidizer, when they are opened up or they are used to burn, what happens during that is basically they tend to give out more amount of heat, right? As they radiate more heat, the energy, there is an overall energy reduce and more amount of exhaust is to be pushed. Now, the loss of exhaust velocity may be balanced by a higher combustion temperature that we are attaining by adding additives and an increase in effective density of exhaust gases. So, we are increasing the mass flow rate at the throat. This increases the mass flow and hence the thrust. The high thrust is applicable for a first stage booster, particularly the boosters that are at the sea level or the work at the sea level, where the ultimate velocity is not as important as much of the thrust at liftoff. And in designing a rocket motor for high thrust and increasing the exhaust density may be preferable to increase in throat diameter and hence overall size of the booster. And the mass ratio is also increased if the grain density is higher. The presence of particles in the exhaust produces the characteristic dense white smoke that we can see everywhere during a booster launch or a rocket launch. When the boosters ignite, the exhaust from the liquid fuel engine is usually transparent because that is burned under stoichiometric ratio. Right? The most commonly used modern solid propellant is based on polybutadiene synthetic rubber binder with ammonium perchlorate as an oxidizer and with some 12 to 16% of aluminum powder, right? So modern day solid propellant rocket motors will be having just highlighted here. The polybutadiene synthetic rubber binder with aluminum perchlorate as an oxidizer. Now, and 12 to 16% of aluminum powder is added as a additive in order to enhance the performance of my rocket. Currently, these type of booster combinations are used particularly under space shuttle boosters, which are discontinued now. Now, these are being again used for my Ariane rockets and Artemis mission, Artemis moon mission rockets, right? And now with this, in the next class we will discuss regarding the additives as well as the grain configurations or the variable possible grain configuration that have to be included in order to identify the best possible combustion rate, right? With that, thank you.
Like, share and subscribe. Hit the bell icon for more updates.